Ladies and gentlemen, good evening and welcome to another session of the Nambani Academy. We are currently running a series of videos and lessons for grade 11 physical sciences. And this is part two of the lessons that we had. We had a session yesterday, part one. So with part one, we tried now to explain in depth key critical concepts that we need for us to be able to explain or answer exam type of questions. But before I get into uh, the nitty gritties of today's lesson, let me just kindly request one of you to greet us back such that we know that I am audible enough, such that I can also know that how was your day. Maybe I should start with you, Mr. Nyokong. How was your day, sir?
Good evening, sir. And
Good.
today I've had a good day. A good day.
No, thank you very much, Mr. Nyokong. Ba Anetse,
Good evening, sir.
evening.
My day was pretty average. How about yours, sir?
Mine was a little bit hectic. There were quite of reports needed, but I did manage, hence I am here. Now, ladies and gentlemen, with that being said, thank you very much. Shanice, kindly open up your mic, introduce yourself, your name, and the school that you are from.
Hi everyone. Hope everyone had a great day. I'm Shanice May and I'm attending Dr. Filion High School.
Thank,
Thank you.
thank you very much, Shanice, and welcome to today's session. Because yesterday you were
Good.
not part of us, but we will try by all means to give you the best possible support that we can do or be able to do so. Ratanang,
So, my day was good.
oh, that is very good. That is very good. Moteo,
Hello, so my day was very hectic as well, but I was able to cope. So
okay.
yes.
No, thank you very much. Lisady, you're the last one, and then you can get straight into today's lesson.
So my day was also pretty good.
No, that is good to hear. Ladies and gentlemen, as a quick recap of what we did yesterday, I am actually going to run over the slides very quickly, only to try and bring Shanice up to speed, as well as us now reminding ourselves what we actually did yesterday. But remember, immediately after this session, I usually send out the PDF notes, and immediately the video of the lesson is available on YouTube for you now to be able to refer and have reference in the near future. But some videos I will not post as they are only for premium subscribers or people like you who are actually paying for this project to be taking place. Now, we started with electricity and we tried now to explain key concepts, and we showed now why do we have to start with electricity. The reason is it contributes around 20-25 marks in the coming June examination. So the idea is let's finish it off, let's wrap it off, let's have a solid foundation. By the time our teachers are doing it at our different schools, at least you have given yourself a head start. For you, it will be just a revision, because now history has taught me that it is now a topic that in most cases is giving us a lot of problems. So these are the key definitions that one needs to know. Ohm's law, power, ionic resistor, non-ionic, and immediately thereafter the application of Ohm's law, which is what we are going to be looking into today or in today's session. So I went deeper into explaining the difference between resistors in series and resistors in parallel. Mr. Nyokon said to me yesterday, but Menier, we've been doing this thing from grade 8, grade 9, grade 10, and we are now again doing it in grade 11. Yes, we are bound to do it again because remember, the key thing is the foundation needs to be solid before one can attempt the exam type of questions. So this slide here, like I emphasized, is a slide that is so important that tells us now the relationship between the current passing on R1 and the current passing on R2. What will happen to the voltage of R1 and R2 provided that R1 and R2 are not the same or are not equal. We further emphasized that now adding more resistors in series, you are actually increasing the total resistance of the circuit. So we later linked this information of a certain number of resistors with what? With Ohm's law. So we are going to try now today and apply the Ohm's law. We came up now with an analogy that we call now South African Police Department, where we say series connection are potential dividers. So they divide now the potential difference. So the potential difference of R1 and potential difference of R2 will not be the same. The reason for that is the resistance is also the same. So now because of that, it's important now to realize that we need to apply these principles. These principles are the principles that are going to assist us in answering the questions in the exam. Let me further move on and say, what did we say about resistors in parallel? We said resistors in parallel are current dividers. So them being current dividers, they allow me to have I1 and I2 not being the same. Because why? R1 and R2 are not equal. But there's one element that I wanted us to emphasize on. That is now the potential difference, which is now V total is the same across each and every resistor that we have in a series, in a parallel circuit. But remember, in an exam, ladies and gentlemen, it is not going to be this easy. Why? Because the examiners are going to combine resistors in series and the resistors in parallel. So the key thing that we are going to do is, in that instance, how can we manipulate the system and still get now to the correct answers? We explained Ohm's law, and this was now a definition or a law, and this law, I would like to say, if the examiners are too generous, they will give it 3 marks, but generally lately we are giving it only 2 marks. So it is also important for you to note that it is a definition. So it being a definition, it says we are expected now to give a proper definition thereof. So a proper definition will be the potential difference across a conductor is directly proportional to the current in the conductor at a constant temperature. So it is important to realize that now the temperature must be constant throughout. That's when now we came up with the formula, which is R is equals to V over I. So V over I is what we call Ohm's law equation. So the Ohm's law equation is what we are going to try and apply today, such that each and every one of us can be able to get the maximum marks. So like I said, this is now just 2 marks in an exam. So remember, it's just a quick refresher course such that each and every one of us can be on par and can know what is it that we need to be doing. We further explained an ionic resistor and non-ionic resistor. Ionic resistor conducts, or it's conductors that obey Ohm's law. Resistance of the conductor is the same or remains the same throughout. I was then asked a question by Motero to say, but say, what if we change now the axis and have I and V? Provided that now the material, which is the conductor, remember conductor? A conductor is just a material. So if the material that we are using is still the one that is ionic, regardless of where or what axis do we have, it will still forever represent now the straight line. Why? Because now the resistance of the conductor remains the same. That is what differentiates between now what? Between an ionic resistor and non-ionic resistor. So non-ionic resistor does not obey Ohm's law. That means it does not follow R is equals to V over I. And in this instance, from the graph, we can easily see that the gradient is changing over and over again. The fact that the gradient is changing, it basically says it is not the same throughout. By so saying, then it does not obey Ohm's law. That is an ionic resistor. So let me give you your 30 seconds for you to digest this, and we can move on now to try and explain other important concepts. Thank you very much. I don't see any questions or raise hands in this platform. So let me quickly move on. So if we move on, it brings us now to a concept that is called power. So the concept of power, we defined it now as rate at which work is done. The SI unit is watts. The initial equation for power is P W over changing T, where now this is what we call work, but we can also represent it in a form of an NH, and this it's measured in joules, where now this is just time and it is measured in seconds. So this is what we want you to understand, because in a multiple choice question they can even give you that, what is this now? This is now equivalent to the SI unit that we call watt. So it is important also to be able to understand what is it that the equation actually explains in terms of the SI units. So joule per second can also be representing what we call watts. But I have embedded somewhere on this PDF file of mine equations for power. So we have P is equals to VI, P is equals to I squared R, P is equals to V squared R. Now the question is, when will I be able to choose the correct equation? Obviously, it's easy for one to say, but if I want to use this calculation, what must I do? I basically just need two variables. So here we must just always have two variables. This is very, very important. So once I have the two variables, I can easily calculate power, I can easily calculate V, I can easily calculate I can easily calculate R. But these equations, as simple as they seem, we are going to link them also to the biggest rule, which will be the Ohm's law. So eventually, after everything else, we must link Ohm's law, we must link these basic principles of resistors in series and resistors in parallel in order for us to apply these equations of power. There are other complex equations or statements or problems that we are going to come across. And this is when now we are expected to explain in terms of power the relationship of resistance, current, potential difference, and how does that now influence the brightness of the bulbs. Furthermore, we explained how to get that maximum 4 marks that I spoke about yesterday. The maximum 4 marks, how does it come about? The maximum 4 marks, it comes by also referring to the equations. So I said the very first thing to do is to check the two resistors that you are comparing. Are they in series or are they in parallel? Once they are in series, the key word is according to P is equals to V squared R. Then that explains now the greater the resistance, the greater the power for the same amount of current, because the current passing at R1 is the same current passing at R2. P is equals to VI. For greater resistance, V also increases. And this links now to Ohm's law, where we said R is equals to V over I. So R is actually directly proportional to V. So once V is bigger, then it basically says once R is bigger, we are also going to have a bigger V. But for what? For the same current, which is I in this instance. So what does this say to me? It says whenever I have to compare resistors in series in terms of either brightness, either the power that is being dissipated, the reference will be referring to equation which is P squared. P is equals to I squared R, and P is equals to VI. But what happens now in an instance where I have to compare resistors that are in parallel? The only key thing is, remember, in science, for a test to be fair, one variable must be kept constant. So in series, we are keeping the current constant. In parallel, we are actually keeping now the voltage the same, and we are only changing the resistance. So it allows us to say that now the only relevant equation, if I am comparing resistors in parallel, it must be P is equals to V squared over R. Why? Because V will be constant, will not change. according to the principles and the basics that we tried to explain to you. But R is the one now that is changing. So the smaller the resistance, the greater the power for the same voltage. That is very, very important. We need to tell the examiner that we understand that the voltage of resistors connected in parallel is the same across the two resistors. So the smaller the resistance, the greater the current according to the equation P is equals to VI. So this was a general approach that one must be able to apply. We further explained now what is the cost of electricity, where we are going to apply it also, the equation, such that you can exactly know what is the cost of running a geyser, what is the cost of amount of energy that is now dissipated if we are paying so much. So all that will be done. But today I want now to add at number 7 the concept of EMF. I will quickly explain it because when I went through the exam guideline, it's something also that they want us to know and understand. So EMF is defined as maximum energy provided by a battery per coulomb. So let me explain this so that we understand. So if you have a battery, that battery will be able to only give you a certain amount of volts. So that maximum is what we call the EMF. So when the battery is not operating or it's not operational, or when the switch is open, we have this maximum EMF. So don't get confused. EMF is also measured with the SI unit, which is volts. And remember, we said volts is just your V. So it is basically your potential difference. But this potential difference, you only get it when you connect your potential difference across a battery. So if we have a battery in the cell, which provides now the energy, which provides the current that we need, it can only give us a certain maximum. If it does not give us that maximum, then the battery is dysfunctional somehow. So it is always critical and important to understand that you will be given a circuit, but that circuit, believe you me, ladies and gentlemen, will have your parallel component, will also have a series component. We are not going to make it easy for you to just only have a parallel or a series connection that you can just easily follow. So the focus of today's lesson, we agreed that it must be an exam type of question. Remember, with us, we do not have time to build up concepts over weeks because at school you have so many contact sessions. So with us, we move directly to the exam type questions, only that we prepare you fully and we give you now hints and tricks of how to manipulate the system. So I have a set of questions that I compiled. What I want to do is the first one I will do, and then the second one you will do with on your own. You send me now your answers. You have the number that we are using. You send it directly to me. You take a picture. I will quickly mark, send it back to you, and discuss the findings thereof. And remember, I am going to now give you a timer for you to do the questions. And if you have problems, then we can further discuss and have a solution thereof. Now, let me give you your 30 seconds for you to digest everything that we have spoken about. And kindly feel free to ask your questions such that we can attend to them before we get into the exam type questions. Thank you very much. I don't see any hands. Maybe it will be advisable for me to say, Ratanang, are you still well? Are you still fine?
Yes, sir, I am.
Thank you very much. Shanice May,
Yes, I am.
thank you. Lesedi,
Yes, I'm fine.
thank you very much. Mr. Nyokong,
I'm still good, sir.
thank you very much. CDT,
Yes, sir.
thank you. Bonolo,
Yes, I'm fine.
thank you. The last one should be Baanetsi. Then we can get into the questions. Baanetsi,
I'm still fine, sir.
if you are fine, I am very happy. Then let's move. I earlier sent you this data sheet. Ladies and gentlemen, the trick is very easy. It is written there in the formula sheet to say current electricity. So all the equations that you need for this section should be here. I do not understand when one does not know which equation to use. It is clear that you are given and you are told these are equations for electricity. When you practice moving on and moving forward, kindly have this at your disposal at all times. You are not cheating the exam because it will be provided in the exam. You must just now be in the way of you understanding how to use the formula sheet. So all these equations that are here, we say is for you to calculate work. At times, they say it's energy. So it's just a matter of you understanding which equation will work best. These equations that are here already, they are equations for power. So already you will be somehow closer to getting to the correct answer, provided you are able to know what to do. Motebe, sorry, Moteo.
Sir, can I just ask, can we
Yes.
choose out of the four, which one we would want to use or?
Thank you very much. It's a very good question to say, out of the four, which one are you going to use? That's where now the science principles comes in. I am going to give you hints now of how to go about that. Once you have the variables, you will see once I do an example kind of a problem. Once you are able to identify the variables, believe you me, then the variables informs you which equation is more applicable or more relevant. So that is the key. We need to find a way of finding the most important variables. So that is what I intend on doing in the next 2 to 3 minutes. But I just wanted to explain here where you find your equations. And obviously, this one is now for parallel resistors, and this one now is for series resistors, and this one is the Ohm's law that we've been referring to. And this one is just for you to calculate current when you are given charge and time. Very, very easy. But ladies and gentlemen, let's check here. All these equations that are here, except this one and this one and this one, or these ones of work, they all have 2 or 3 variables. So what does this say to me? It says to me, as an application, maybe I must get a new sheet for you to see this properly. Let me get a new sheet. Let me get a new sheet for you guys, such that we can follow exactly what I want to explain. Let's move to the equations again. I believe the understanding is clear. So the hint that one is going to give is, this is now hints on applying Ohm's law. Hint number 1, follow the current path, comma. The current path must include the question. Follow the current path. The current path must include the question. I don't know if it's making sense. I will write it now. Follow the current path. The path must include the question. Or we can say the variable, or we can further say the resistor, because it will always refer to the resistor in question, the resistor. So when I do this, in that path of mine, I must include the question, that resistor that the examiner is asking about. Calculate the power dissipated by R1. Calculate the current passing at R1. So it means R1, it will be a point of reference. Follow the current path. The path must include the question, which will be the variable or the resistor in question. Hint number 2 is to say 2 variables. Okay, let's see one. One variable will always be given. Definitely. Noma kanjani. One will definitely be given. The examiner must give us that one, unless otherwise. But remember, we said how many variables do we need? We need a maximum of 2. So one will be given. Now, this is the science that I spoke about at number 3. One variable will be given, but hidden. It is there, but it is hidden. So how do we get this one hidden variable? Apply, sorry, apply basic principles of series and parallel resistors. Apply basic principles. So these basic principles are going to help you to get now what? To get the variable that is hidden. So now that we have two variables, it's easy. Apply Ohm's law. Then that will be the final step of getting to the answer, which is apply now Ohm's law. I want to say Ohm's law, but it can be any relevant equation. So let me also add any relevant equation. This is not restricted only to Ohm's law. You can use the very same principle for you to calculate now issues of power, calculate issues of work or the energy that is lost, everything in that matter, if only we follow this particular hints on how to apply Ohm's law. Follow the current path. The path must include the question, which is the variable or the resistor. One variable will always be given, ladies and gentlemen, always. But one variable will be hidden or will be given but hidden. This is what I want to say, especially at bullet number 3. This is what differentiates a learner who's going to get a level 4, level 5, level 6, and so forth, because it's now the application of the basics. This is what I usually say, apply the basic principles of science. Once you are able to apply the basic principles of science, then everything becomes so easy for one to be able to understand. So I want us to have these hints we are going to apply in a problem that we are going to have and see that now isn't it assisting? Isn't it maybe somehow making things a little better or easy for me to understand? So with this being said, kindly ask me questions relating to the equations and also relating to the application of Ohm's law. I don't want us to jump this section because this section is the one that we need in order for us to get the maximum marks. So I am going to give you your desired 30 seconds for you to digest this. Feel free to ask questions, and once the 30 seconds is done, then we move into the question that we have for the day. Thank you very much. I do not see questions. I believe everything is clear. Let me get into the question of the day. Like I said, the first one, I will do it just to show you how to approach this particular questions. Is the diagram clear on your side, ladies and gentlemen? Ladies and gentlemen, is the diagram visible on your side?
Yes, sir.
Thank you very much. Now let's start and get into it. This is a previous question paper, hence I left it as question 9. It says in the circuit diagram below, the internal resistance of the 6V battery and the resistance of connecting wires are negligible. So we are told that we have a battery that has now 6V volts. We ignore internal resistance, we ignore the resistance of the cable, we only focus on the resistors that are given. The very first one says state Ohm's law. Ohm's law is just a definition. I'm not going to bother you and waste time with that. Remember, definitions are non-negotiables. So at 9.1, the answer should be the potential difference across a conductor is directly proportional to the current in the conductor at a constant temperature. So this becomes now an easy 2 marks. I'm not going to bore you with that. Now, ladies and gentlemen, let's check. 9.2, switch S is open. There is S. I must get a highlighter for us to understand. There is S. There is the current coming, passing at 6, also passing at 4, coming there, and now it goes back there. But now the switch is open. Can you already see by following the current path? Already I am able to tell that it basically says when the switch is open, no current is flowing. And if there's no current that is flowing, what does it say? It says the battery is operating at maximum. So bullet number 1 on the hints also assists when the switch is open, when the switch is closed, you can easily see the flow of current thereof. So the flow of current thereof is being informed by this yellow line that I drew. I said follow the current path. I do not know the question, but now I just know that the current will flow from this side there until point B. But now the question says, a voltmeter is connected across points A and B of the switch. What will be the reading of the voltmeter? Ladies and gentlemen, let's go back. EMF, the maximum energy provided by the battery per coulomb. What does this say? It says the battery is only operating at maximum when we have a switch that is open. So operates at maximum when the switch is open. So once the switch is open, we get the EMF. What is the EMF? The maximum energy provided by the battery. So I can come back here and say fine, but now I know that when the switch is open, there is no current that is flowing in the circuit. So what does it mean? It means now the only maximum voltage I can get is now what? It's now at 9.2, it will be 6 volts. Hence it is just 1 mark for that matter. Why? I understand checking the yellow path that but now my current will not be able to pass at A and B. So if my current is not passing at A and B, then I do not have the current flowing in the circuit. Then my battery must operate at maximum. My battery must operate at the level of the EMF. Questions relating to 9.2. Mr. Nyokong, questions relating to 9.2?
I'm good, sir.
Thank you very much. Lesedi,
I'm good, sir.
thank you very much. If we are all good, then let's go further and explain again. When switch S is closed, now they decide to close switch S. So I am going to put again my yellow highlighter for me to be able to close the switch. What does it say now? It says the current will be able to follow. So I have current passing at X, I have current passing at 6, I have current passing at 4 ohm. I explained to say the examiners are not just going to give us a straightforward circuit. When I check the position of X, let me get my red pen here. The current passing at this point, if I were to put an ammeter here, the current passing here, which will be I total, can I easily say it will still be the same current at X? Yes, because I can easily see that now from following the current path. The current that is coming at A here is actually the same current that is passing at X. So I'm just analyzing the circuit. But I definitely know that I am going to have the current passing at 6 ohm and a current passing at 4 ohm. It is now what? Applying those basic principles. Because at the junction here, at this junction, the current is dividing such that it can supply current to 6 ohm. It can supply. Ladies and gentlemen, I am not answering questions. I am analyzing the diagram given to me. Let's go back. Follow the current path. Done. Bullet number 2, one variable will be given. We are given the total voltage. We are given 6 ohm resistor. We are given 4 ohm resistor. If this is now the question at X, then something must be given to us which will be V1 at a certain instance. But why? Because analyzing the circuit will allow me to use this principle that says, fine, I have one variable that will always be given. One variable will be given but hidden. That is where I want to go. Hence now I need first to analyze this particular circuit. Let's go to 9.3 and 9.3.1. It says the current in the 4 ohm resistor is 0.9 amperes. We are told this current that is passing here is 0.9 amperes. Ladies and gentlemen, where are we in the circuit? Calculate the current passing in the 6 ohm resistor. Can I calculate the current passing at 6 ohm resistor? No, I cannot. But I can easily say I am at 6 ohm resistor. Do I have R? Yes, R is given, it's 6 ohm. Do I have the current? That is what the examiner is asking. So do I have V? No, I don't have V, but if I can use the information of 4 ohm, because at Let me write it here. At 4 ohm, what we have? We have R, which is equals to 4 ohm. One variable will always be given. Furthermore, the current is given 0.9 amperes. Can I calculate V? Yes, I can. This will be the application of Ohm's law as per the understanding. So I am going to substitute. I have this one as 4, this one is V, this one is 0.9. When I do the mathematics, I find something like 3.6 V. 3.6 V. I have the V now. Let's go back to the hints. One variable will always be given. Let's go back. One variable is there, which is the 6 ohm. It's given. Now, one variable will be given but hidden. Apply principles of series and parallel resistors. So one variable is given, which is 3.6 V. How is it given? It is given because we said when we have resistors in parallel, the V of 1 is equals to the V of 2. So I can easily now say, fine, if that is the case, the V at 6 must also be 3.6 V. One variable will be given. Always. One will be hidden. Apply principles of basic, parallel, and series resistors. So now that we have this V, we can apply Ohm's law again and say, fine, Ohm's law, we have 6. We want the V is given 3.6. We want the current. You do the mathematics. I is something like 0.6 amperes. So we're not going to be able to get to this because V is what you always needed to have. For 6 ohm, also for 4 ohm. So we were given the information of R at 4 ohms, the current at passing at 4 ohms, which is 0.9. Then it comes to a point that I can use the application of Ohm's law. Immediately thereafter, I can be able to say, but when I apply the basic principles, is that now the V at 4 ohm and the V at 6 ohm must be the same. Why? Because they are both connected in parallel. How do I know? It is this division that is taking place at this junction here. So at that junction, once it starts to split, definitely it is an indication that the two resistors are connected in parallel. Let me give you 30 seconds to digest and kindly ask questions. Bunolo, anything, comment, suggestion?
Nothing from my side, sir. Everything is fine.
Shanice?
I'm great, Munir. Everything's cool.
Thank you. CDT? Muteo?
Everything is good, sir. I
Thank
was a bit lost at first, but I understand now.
you. Understand now. Thank you. Ba Aneti?
Yes, sir.
I'm still fine, sir.
Okay.
And
Okay. If you are fine, Ratanang.
I'm good, sir.
If you are good, I'm good. Then the last person should be Lisedi.
I'm good, sir.
Okay, then. If you are good, let's try 932. The total current in the circuit. That's for 2 marks. It's easy, ladies and gentlemen. We have calculated that the current passing at 0.6 amperes. To get the total current, it's easy. I am going to use red highlighter. Let me try green just to indicate something. This current that is passing here and the current that is passing there, when it gets to this point, it comes out as the total current. So basically, what must I just do? Very easy. I must just add the current passing at 6 and the current passing at 4. That should give me my total current. So I total will just be I passing at 6 plus I passing at 4, and this will be 0.9 plus 0.6. This will give us something like 1.5 amperes, and then you will get your easy 2 marks. 1 for correct substitution of everything, 1 for the correct answer with the correct SI unit. That is very, very important. Now, ladies and gentlemen, at 933, it says calculate resistance X. Okay, let's go to X. Do I know the current passing at X? Yes, I know the current passing at X. How do I know? I am going to use the green highlighter again for the purpose now of knowing that the green in this instance will represent the actual total current passing. So let's take the green and move. What is the word? Follow the current path, and the path must include the question. So it means it must include the X now. So can I now write the variables that I have at X? Yes, I know that the total current passing there is 1.5 amperes. But what else do I need? I need to have the V, but I am not given the V. Bullet number 2, one variable will be given. What is that variable in this instance? It is the I total. Can we get now the one that is hidden? Yes, you should get the one that is hidden because we are now at 9.34. 9.33. Where are we? We know now V total is equals to Vs plus Vp. What is Vs? Vs is actually V1. It represents now the voltage of what? Of the resistor that is now in parallel. What is V total? V total is just 6. That is the one given by the battery. So we want Vs. In this instance, I will write it V1. What is the potential difference that we calculated for parallel connection or parallel branch? We said it is 3,6. So it is basically 6 minus 3,6. This will give us V1, and V1 will be something like 2,4 V. So V1 is actually the one that was hidden in this instance. So I have the current passing there. The examiner wants the resistance of X. then it basically says I need now to find the V. So it will always be I, V, and R. So once you've found the two variables, because if I have the V and the I total is given, it becomes easy to say, but now at X, what do I have? Do I have R? No, R is the question. Do I have I? Yes, it is 1 comma 5a. Do I have V? I just calculated to be 2 comma 4. Can I use Ohm's law? Definitely. R is equals to V over I. This becomes now Rx. This becomes 2 comma 4 divided by 1.5. Then you get your V as of something like, sorry, your Rx as something like 1.60. So I am going to pause and also allow questions such that we can know we are on the same page. So your 30 seconds starts now. I am only teaching you how to approach this in an exam with simple hints of what one can do and what one can follow. If you follow this, ladies and gentlemen, you are on the right track of understanding how to go about electric circuits. Follow the current path. The path must include the question. I applied that here at 9.3. I applied that at 9.32. I applied that at 9.33. How difficult can it get? It will not get any difficult because I must just remember the sequence that one needs to follow. Follow the current path, include now the question, check for the one variable that is given. Immediately thereafter, check now which variable is hidden. Once you understand that, you must apply the basic principles of series and parallel. Let me start with you, Mr. Nyoko. Do you now understand the importance of having those basics that I emphasized yesterday? It was not only for the repetition of content or the concepts that you are taught in grade 8, grade 9, grade 10. It's actually solidifying the contact process that we actually have in terms of fully understanding the approach to answering the questions. So what's your take, Mr. Nyoko?
Yes, sir. I now understand.
Thank you very much. So one cannot just assume that you guys know these things. We must do them such that we solidify our foundation. Any comments, ladies and gentlemen, relating to 9.3? Let me start with you, Lesedi.
No, sir.
No comment. Thank you very much. It is exactly 1906, and I want us now to have almost about 20 minutes for you to work on your project, not project, your question that I'm going to give, such that you try now to apply this, and then we are able to, what's the word, to do remedial. And obviously I'm going to send out the PDF notes. Then you do that one later or even tomorrow. You send it back to me such that I can actually mark and see the effort that you took to go into that. Motero,
Yes, sir. I just want to ask about 9.3.3, right?
yes.
So the V1 and the V1 is obviously the 3.6 and the V total. Wait, sorry, no. Didn't you say for parallel that they are equal? Wha- Unless, wait, is the X in series or is it in parallel?
Thank you very much. Nice question. Let's check. What is the current passing at X? It's the total current, ne?
Yes.
Then it means it is in series.
Oh, okay.
Now, let's go to that huge dot that you see there at the junction between 6 and 4. Ne?
Yes, sir.
The current divides into two.
Okay.
The one is passing at 6 ohm, the other one is passing at 4 ohm.
Yeah. Okay, sir.
Yeah. So what does this say? It says in this circuit, I have two sections. A section that is now for parallel, which is 6 and 4, ne? And a section that is series, which is X. So now for me to calculate the potential difference at X, I must consider the total potential difference of the circuit. That will be the 6 provided by the battery. That will be for parallel, that is now 3.6. But the potential difference at 6 ohm is 3.6. Ne? The potential difference at 4 ohm is 3.6. Why? Because 6 and 4 are in parallel with each other.
Oh, okay, okay. Thank you, sir.
Thank you. And the other hint should be when you add your voltages, they can never be higher than what the battery can give. So if we say we have 3.6 at 6 ohm and 3.6 at 4 ohm, and we have 2.4 at X, everything combined must now is going to be over 6. So hence now the important part of the slides is apply the principles of physics and the basic principles of series and parallel. That's the reason why I want you to be aware that it will only be 3.6 for parallel and then 2.4 for V at X. Then you just apply Ohm's law again.
Okay, thank you, sir.
Thank you very much. Now, ladies and gentlemen, let's go to 9.34. Energy dissipated by resistor X in 1.5 minutes. We said, let's go back to the formula sheet. T in all of this, time must always be in seconds. I think I elaborated also somewhere to say time must be in seconds when we talk of energy and power. That is very, very, very important. So the catch also here is now we must convert that 1.5 to seconds. So how can one do that? We must just multiply this by 60. It will give us 90 seconds. So time is given. Where are we in the circuit? We are at X. So let me duplicate this such that we create now enough space. Duplicate. Because if we are at X, then we are going to need to have an equation that is going to assist us to calculate the power that is passing there. Because you asked me, how does one choose the correct equation? And I said it entirely depends on the information that is given to us. So the information given to us, it works as a guideline in terms of how and how can we get the correct answer. So I'm going to leave this information of X here because we are going to need and move on to 9.34. So at 9.34, we need now an equation. Let's check the equation we have. We have W is equals to VQ. We do not have anything that has to do with Q. We are not informed of that. So the fact that we are not informed of that, that equation will not work. We further move to equation number 2. V is equals to, or W is equals to VIT. That looks like it will work because we have the V, which is 2,4. We have the current passing there, which is 1,5, and we have the time, which is 90 seconds. Will W equals to I squared R changing X also work? Yes, it should work because we have the current that is passing there, which is 1,5. We have the resistance that we calculated, which is 1,6. And we have now time, which is 90 seconds. Will W is equals to V squared changing T over R work? It will work because we have V, which is 2,4. We have T, which is 90 seconds. We have R, which is now 1,6. So when you ask a question of how can one choose an equation, to me, it basically relates to the information and the data that you have. So I am going to choose 1, 3, 4. I'm going to choose W is equals to VI changing T. And this becomes easy. 2,4 for V, 1.5 for the current that is passing there at X, and the time, which is 90 seconds, and I have something like 324 joules. So the 324 joules is actually the energy that is dissipated by a resistor X. At 9.4, the 4 ohm resistor is hotter than the 6 ohm resistor after a while. Explain this observation. Now, it is the application of power. It is now us explaining in detail how one can go about answering these questions. Yesterday, when I explained this, it seemed like it is just an add-on, but we actually ask such questions. The examiners actually prefer to ask such questions. How do you get your maximum marks? It's very easy. I said now you must check, is 6 and 4 resistors that we are comparing, are they in series or in parallel? Definitely in parallel. Then what must we say? Very easy. According to P is equals to V squared R, the smaller the resistance, the smaller the resistance, the greater the power. The greater the power. That is the reason why 4 ohm is getting hotter than the 6 ohm resistor, because the potential difference is the same. is 3.6, 3.6, but the resistance is smaller. So when I check this equation, I am actually going now to do what? I am going to divide with a smaller number. That smaller number will give me now a greater power. But I said we must further explain to say this is actually for the same voltage. The voltage at 6 ohm is 3.6 V. The voltage at 4 ohm is 3.6 V. So the voltage is actually the same. I can easily further now and say, but now for the smaller the current, the smaller the resistance, the greater the current. The greater the current according to P is equals to VI. And this now results in greater power. So once we have greater power, obviously it will get hotter because it is now dissipating a lot of power. Then this is now how I will get my 3 marks, because I have told the examiner or the person who's going to mark this script to say I am referring to the equation P is equals to V squared R. Why? Because these two are in parallel. Why can I not use P is equals to I squared R? I cannot use that one. Why? Because the current is changing, the resistance is also changing. So for a fair comparison, one variable must be changed. You cannot change two variables at the same time. I hope this question is opening your eyes in terms of how to answer and how to approach certain questions that will be part of the examination. I was emphasizing that we cannot use P squared R. Why? Because the current is different, 0.6, 0.9. The resistance is different, 6 and 4. So it becomes now an unfair comparison because two variables are changing. So hence I said now to you, some things you just now know when to apply and what to apply. Ladies and gentlemen, with that being said, I believe I explained everything in detail that relates to this particular problem. So I want you to ask your questions before we can actually get to the question that we are going to do. It will be a very nice quick question. Remember to send me your answers. I will quickly mark from my side and explain. So it is exactly 1920. So I'm going to give you about 15 to 20, 10 to 15 minutes for you to do this particular problem. And once you are done, then at quarter to, not at quarter to 22, we will start marking, explaining it such that you can easily mitigate or solve the challenges or problems that you actually do have. So with that being said, let me give you your 15 minutes of this question. The 15 minutes of this particular question. Maybe I must just enlarge it. Let me just enlarge it. There we go, so that it can be nice and clean. So it is 18 marks. So I am going to give you your 15 minutes. Let's make it 13 and your time starts now. Kindly send me your answers to my personal WhatsApp, then I can quickly mark them. Thank you very much. Ladies and gentlemen, thank you very much. I only received one response. I'm waiting for others. My personal interest is at 8.4. So it's at 8.4. Let me check. 8.4, 8.4. Okay, my interest is at 8.4. So I want to discuss, but I can only give you a maximum of 3 minutes because it's exactly 1937, so that at least you can have the 20 minutes to try and discuss. So I'm giving you 3 minutes. Thank you. I've received a response here. Thank you very much. Let me give you extended 3 minutes such that I get all the answers. Thank you very much. More responses received. Let me look on this one that recently came in. Let's see. Let's discuss. But I am very happy for the efforts that you took. Remember, It's a learning curve. We practice, and until we get everything right with proper understanding. Ladies and gentlemen, 8.1, 8.2 is 4 marks. Power is defined as the rate at which work is done, and then Ohm's law is a law that we just spoke about recently. So I'm expecting each and every one of us, sorry, to actually get this easy 4 marks. So I'm not going to bore you with the definitions. It's something that you just now read and recall, and you just give it to the examiner as per the exam guideline. Now let's look at the circuit that is given. When I look at the circuit that is given, I see a lot of information, and the information that one will use. But can I simplify this circuit in such a way that I fully have an understanding of how to go about it? Let me see. I'm just going to try and redraw. That's where the problem came in. Or maybe I should use green to explain. Bullet number one. And bullet number one says what? Follow the current path. So I am going to move from here. The switch is now closed. Move again there. But now at this big green point, my current is now dividing into two. So it basically says I have now the current that is passing at 4 and the current that is passing at 6 ohm. But now let's check this. Analyzing the circuit is very important. Let's check this. The current passing at 6 and the current passing at 10. What can we say about that? Let's say the current passing at 6 and the current passing at 10. What can we say about that particular current?
So I want to say that I feel like it's not right, but I wanted to say the current is the same, but it's not.
It is the same. Check the current path. It is the same. Why is it the same? Because now
It's
check the green. So when you check the green, you are basically getting the same line that is passing at 6 is actually the same line passing at 10. So that is already a hint to me to say, but now applying the principles of series and parallel, 6 and because the current passing at 6, let's go back to this slide. The current passing at R1 is the current passing at 10 ohm. So 6 and 10 are actually in series with one another. Hence, follow the current path. So I am going to draw this circuit nicely and say I can combine 6 and 10 to become one resistor, and that resistor will be a 16 ohm resistor. It will make sense because the principle of resistors in series is that they share, not share, the current passing through the resistor must be the same. So follow the current. The current path allows you to distinguish whether you have a parallel or a series circuit for that matter. So let me draw this circuit, a simple circuit, and then I say this is 8 ohm. I say now this is going to be my 4 ohm, and this is going to be my 16 ohm, and everything there becomes now nice and simple. Why? Because the examiner is only trying to assess me in terms of thinking of, but now the current passing at 6 and the current passing at 10 is the same current, hence is the same green color throughout. It didn't break anywhere, so I just combined the two and created now a new problem which is called 16 ohm. Now the ammeter is there by 4, it's there at 4, so they want us to calculate the current passing at 4. What are we giving? We are giving the 4 ohm resistor, and we are given now 36 watts. So P here is actually 36 watts. So one can easily say, okay, fine. Now at 8.3, I can easily say I am at 4 ohm resistor. The reference, ladies and gentlemen, is always important. Where are you in the circuit? So I said now P is given, one variable will always be given. So P is equals to 36 watts, R is equals to 4 ohms, and I can easily calculate the current. That will be an easy 3 marks for us to be able to get. Let's check if we are doing it the right way. P is equals to I squared R, because the current is not given. So P is equals to I squared R. Sorry, that's not how I do things. I must write P is equals to 36. R is equals to 4 ohm. The question is now the current. Can one say P is equals to I squared R? Yes, it is the formula from the formula sheet. This is 36. This is I squared. This is 4. You do the mathematics and eventually you find that you have your 3 amperes. So the current passing at 4 here is 0. Sorry, it's 3 amperes. So I am also going to write it here. It is 3 amperes. But from this new designed circuit of mine, I can easily see that the 3 is passing only on the 4 ohm resistor. It's not passing on the 16 ohm resistor. Can I get the current passing at 16? Definitely. If I can get the total current of what is passing at 16, then I am done with the circuit, because I just need to know one hidden variable. So the hidden variable in this instance, let's take the green again. One hidden variable here, it is the I total. So once I know the I total, I can answer all the questions that are here. Now, ladies and gentlemen, let's do this to answer 8.4. Calculate the reading on V1. Okay, on V1. Now, where am I in the circuit and what do I know about resistors in series? If I can get the V of 4, I know the V of 4 must be equals to the V of 16. How do I know that? Basic principles of series and parallel. So I am going to go now at 4 ohm again. But this time around, I am interested in getting the V. Why V? Because I am going to get that V of 4. But this V of 4 is actually equals to now what? The V of 16. Why? Because 4 and 16 are connected in parallel. So I am at 4 ohm again. But what do I say now? P is equals to V squared R. The P is given 36. The V squared is what I am looking for. And this is the 4. I do the mathematics. I get now the 12 volts. But the 12 volts is at now what? At 4. But 4 and 16 are connected parallel to each other. So if that is the case, can I say now at 16 ohm, what do I have? I have V, which is equals to 12. I want the current. I am now knowing that definitely this should be 16 ohm. Can I use Ohm's law? Definitely. R is equals to V over I. And this is 16. V is 12. We want I. And let me remove this. We want I. So I is 0.75 amperes. Okay, fine. But now that is the current passing at 16. Let's go back to the original diagram. Remember, 16 is a combination of 6 and 10. I have 6 minutes to finish this. It's combination of 6 and 10. So if the 0.5 is passing at 0.75 is passing at 16, what is it that is passing at 6? 0.75. What is passing at 10? 0.75. Because now that is the sum of the two resistors combined. So I am going to say here 0.75 amperes is actually passing there. 0.75 amperes is actually passing there. Why? It is the same current that is passing at 6, is the same current that is passing at 10. Is the same current, ladies and gentlemen, that is passing at 16. But 16 is a combination of 6 and 10. That's how we make it now look very easy and straightforward. But we have not answered the question because the question says calculate the reading on V1. So where are we in the circuit? We are at now 10 ohm. What do we have that is always given? 10. What did we calculate current? Yes, 0.75 ampere. Can we calculate now V? That is the question. Can we apply Ohm's law? 100%. R is equals to V over I, which is now 10, which is now V is what we are looking for. Current 0.75, and you find your V is equals to 7.5. 7.5 V. So that is until now 8.4 or 8.4. The reading on V2 will become easy because we have the current, which is 0.7 plus the 3 ampere that will be here. So the total current will be 3.75 amperes. So 3.75 amperes. This one becomes easy. You have R, you have the total current, then you can calculate V. Ladies and gentlemen, I am going to pause at 8.4. Remember to also send me your 8.5, your 8.6, but I think the one that was more complex was the 8.4, because you had now to move and understand that in actual sense, when you have resistors connected in series, you can actually add them and have one big resistor. So I am going to open up. We are left with 3 minutes for Mr. Nyokong to give us a feedback of today's session, such that we can be able to close the session, and maybe things that we call takeaway, things that you can take from today's lesson and apply in the near future. Remember, you will still get the PDF notes. You'll go through it. You will start now practicing. I have given you the platform where to get previous question papers. NambaneAcademy.com. That's the website. Play around with it. There's a lot of nice things that you can get there. So, with that being said, Mr. Nyokong, the platform is yours.
Hello, sir.
Hello, sir.
Like today was nice, sir. Like I learned a lot of new things. I learned how to apply Ohm's law in like a very new way. I didn't know that we were supposed to like add resistors like that. Like I never knew that. Some of my answers were wrong, but then some of them were also right. Uh, yeah, like I learned a lot today.
Thank you very
Thank you,
much,
sir.
sir. Thank you very much. Baneti,
So I learned a lot today. I think I learned from most of my mistakes because I did a lot of mistakes. I'm not going to lie. And today's session was okay, I guess. So. Thank you, sir.
thank you very much. Bonolo.
So I learned a lot today as well. I did make some mistakes, but I learned from my mistakes and I can see how to go about with the questions. And yeah.
Thank you very much. Because, like I said, it's better to do the mistakes now. Send me your answers, we correct, and then we build now this strategy. Remember, science is not something that you can just get over a day. So you'll have all these nice principles, these nice approaches, but the application thereof. So hence I said, visit the website, get other questions. I will also add a few on the PDF that I'm going to send you. Kindly do them such that you can easily test now the skill. There isn't anything new to teach from yesterday. There isn't anything new to add from today, because I can give you another different set of questions. The approach will still be the same. It's just an issue of you understanding where are you in the circuit. So this thing of following the current path, one variable is always given. It must be a pattern that you practice day in, day out. The drawing on top of the circuit itself to know where are you. It is a system. It is a systematic approach for you to know where are you in the circuit. And remember, follow the current path. Shanice?
So yeah, today was very applicable to what like we've done like last year. This is like the same things we did last year in grade 10. So, and you made it much more easier. Like you explained it so nicely. And yeah, I saw my mistakes and yeah, I've learned from it. Thank you so much
Thank you
for
very
today's
much,
lesson.
Shanice. See you again next week, Monday. Uh, Moteo?
Yes, sir. I'm still a bit confused with 8.4.
Mm,
Well, not necessarily there at 8.4, but how you got to the 3.75, sir. At the other
oh, at the
what do
diagram.
you call it? Yes, sir, yes.
Okay, remember the current passing at 4 ohm, we calculated it to be 3 amperes, ne?
Yes, sir.
and then you just calculated the current passing at 16 ohm as 0.75.
Oh, okay, okay,
So at that huge red point, they come together ne, to become the total current of the circuit.
okay.
So
Thank you, sir.
it becomes the 3 plus now the 0.75.
Okay.
Thank you.
Thank you. Thank you
But you
very
have not
much.
given me the reflection of today.
Oh, I'm sorry. After what you explained now, I now understand what's going on. This lesson was very thorough and detailed. Yes.
Thank you very much, Moteo. Ratanang,
So I learned a lot today. The only place where, like, the only sum I got wrong was 8.4. That one confused me a bit.
okay.
But I think the more I practice, the better I'll do.
Okay, thank you very much. Lesedi, close it for us at exactly 20:03. It's time for us to rest. It's work tomorrow again.
So this lesson was very insightful. I learned how to, like, especially from my mistakes in 8.4. I now see how to apply, like, following the current path, and also using those hints on how to answer the question. So yeah.
Okay. Thank you very much. Ladies and gentlemen, from me to you, thank you very much. And remember, the recording of this video will be available on YouTube. It will be the only one that is there under electric circuits, only for purposes of reference, because you can watch, refer, and basically check if you are doing everything right. So, with that being said, ladies and gentlemen, thank you very much for entrusting me. Thank you very much for you being here and taking your time. It's not easy for one to be here from 16, what is this? From 6 p.m. to 8 p.m. Monday and Tuesday, but now the commitment thereof will definitely pay. So, from me to you and the rest of the team, thank you very much. Have a lovely day and enjoy the rest of the week.
Thank you.
So
Bye, sir.
Thank you,
Thank
sir.
you, sir. Bye.
Bye, sir.